Hey everybody, this is Miss Fred. I'm going back over the identities we learned in class. All right, so we're going to start with the Pythagorean theorem identities, and I'm going to go over some questions the students had yesterday. Here we go. So remember, the entire foundation of trigonometry is based on the Cartesian plane and the geometry that you start with any random point here. So as you know, I usually pick in quadrant 1, even though you could pick in quadrant 4. And you know that you're going to draw a perpendicular down to the x-axis. You get a nice triangle here. We have angle theta, which is the reference angle. Theta is the reference angle. And then we know that these side lengths are x, y, and then we're assigning radius 1. Okay, so we have a couple of things we can prove from here. One of the things we can prove is that sine theta is equal to opposite over hypotenuse, and cosine theta is adjacent over hypotenuse. And so we get that nice identity, which even though I haven't called it that, it really is an identity where you can do direct substitution for regular xy and then the trigonometry. And you're pretty well versed on that at this point. In fact, I think most of you could prove it to me if you understand this idea. Okay, then next, because we have a right triangle, the situation is we have a right triangle, we can use the Pythagorean theorem. Okay, and why is this useful? It is useful because we have an imposed circle on top, a superimposed circle on top of this embedded triangle, which of course is the unit circle, and that is because we have chosen for this to be radius 1, which means every radius on the circle is going to be radius 1. So what are we building? We're building the equation of the circle. So build equation of the circle. So because it's a right triangle that we're building off of, we have leg squared plus leg squared is equal to the hypotenuse squared. And so when you do the direct substitution in, the trig form of the circle looks like this, and then we derive all these different types of identities straight off of this particular identity. Okay, so just reminding you how that works. So then I derive the other two formulas using this base formula here, and we're going to derive the other two. So we have the first one, and then we're going to build number 2, and then we're going to build number 3. So the way I asked you to start it was to just write these down, and then when I divide, and this is important because I always hear, where did you get that from? When I divide by sine squared theta or cosine squared theta, I'm doing it because I choose to do it, because other forms are useful. So for this one, I'm going to divide by cosine, but of course you could divide by sine. It doesn't matter the order. You do these in, and you're going to go all the way across because, you know, it's an equation. And then you now derived your other equation. So it's a form of the circle. I mean, that's essentially, because remember, you don't change the original equation. It's just you've manipulated with algebra. So this is 1 plus, and then sine over cosine is tangent, even though it's squared. And then you have 1 over cosine, which is secant squared theta. Okay, so now we've got our second one. Okay, then we're just going to do the same thing, only with sine squared this time. And we get this time cotangent. So we're going to get cotangent squared theta. And these are based on the identities. Okay, so if you're not understanding that, you need to ask me in class. Okay, this is really testing to see if you really understand those relationships. And then this one is cosecant squared theta. And now I have my 3 base equations, and now I'm going to derive the other 6 of them. So I'm going to go over and change my slide. And I have this. So we have just worked on finding these 3 here. So it's a good idea to keep all the stuff all the formulas on one sheet of paper. So you may want to start like a little cheat sheet. Okay, so the question is, how do students remember these? Okay, I've never come up with a perfect way to remember these, so you need to come up with a way because you need to think of these quickly. I know you're looking at your notes, but again, like you've got to apply them. So I don't know if there's some way that you can take the letters. So all I did was just take S, C, and then instead of 1, I'm looking at it like as if it was an I. Okay, so like little ways that you can remember this. So tangent, like tangent, I. So it's going to be like the word tis if you want to do that, and then I, C, C. Let me see if there's a pattern here. We're going to check it out. Sine, cosine, and then I. So I don't know if your brain can have a way to memorize those things, but check it out. And then share with me if you come up with something. Alrighty, so the question is, on your Delta Math, what's the fastest way to complete one of these? And yesterday, all I was doing was really just giving an introduction, which is why I only gave you 3 or 5 problems in your assignment, just to kind of get used to these, just how they look. Let's talk about efficiency now, okay? All right, so this is similar to a problem like you had in Delta Math. So what I do is I look at the following. Remember, if you went to the video is going to give you huge proof. I don't need it that detailed. Okay, so I'm going to show you a shortcut. So here's the expression that you have. I'm going to start looking for secant squared x. So I'm going over here to secant squared theta, right? It's the same thing. And then I have tangent squared. And oh, look, they're in the same identity. So this is the one I'm going to manipulate. So I'm going to rewrite it down here. Tangent squared theta. Remember where they came from, okay? Just remember that they're not random. Okay, now I'm going to change this equation to look like this expression, and then I can do a direct substitution. All right, so if I want secant to be positive, I'm going to move tangent to the other side. So this is tangent, and then you have it. And you can see, even though I haven't finished it, that the answer is going to be 1 on this one. So this is 1 is equal to minus tangent squared theta. Okay, so then there's 1. Okay, so we'll do another one just to make sure you're okay. Okay, we have the next one, so go ahead and write that one out. All right, so again, I'm going to look over at the 3 that I've built and the problem. So I need cosecant this time. So look, there's cosecant, and then I need minus 1. So I'm going to subtract 1 from both sides, and since it's the bottom one that's here, that's nice. I don't have to rewrite it. And then it's cosecant squared theta, and then minus 1. So you can see this one is cotangent squared. And that's basically what you have to be able to do, okay, for the Pythagorean identity, so you can use it later on. So remember, this is just a skill that we're learning right now, and we're going to use it to solve equations. Okay, moving on. So these were the sum and difference angle formulas that we looked at yesterday. And as a reminder, I uploaded YouTube videos in your Google Classroom. So if you wanted to look at that proof, you could. But in the meantime, you need to know how to use these and be able to identify. And just a couple things I want to point out to you. Sum and difference. So inside you're affecting the angles here. And then for cosine, I want to point out that when you add the angles together, you're really subtracting this combo, these combinations or these terms. Okay, so make sure that you realize these have opposite signs. So you might want to put that somewhere in your cheat sheet. Signs for cosine. I know signs, we got to be careful what sign we're talking about, right? So signs, like values of signs, right, for cosine. All right, now we're going to derive the other 2 sum and difference angle formulas. And if you ask me, there's more? Yeah, there's always more. So we have what missing on here? We have tangent missing. Okay, so we're going to level it up. So I've now added them to this collection of identities, so you might want to copy that down. Now I'm actually going to go through the proof in a couple seconds. All right, we're going to do that proof now. So remember, what is the relationship of tangent? A couple ways you can describe it, but the most useful way, since we have sine and cosines, would be that type. So we're going to replace tangent with the following. Tangent is the same thing as sine. So it's sine a plus b over cosine of a plus b. And then we're going to expand everything out. So you come over here and you look for that. Oh, this is the one right here. So you're going to substitute this portion. And then you're looking at the bottom. So you will substitute this portion. And then we're going to do some simplification. Now, we're trying to get to the ultimate goal. To remind you, we want this formula right here. So when I examine the goal, I see that there's a 1 on the bottom. This is problem solving that you're doing, and problem solving in mathematics is more important than anything, in my opinion, because the skill of problem solving is what you're going to carry on to your classes, your life, and all that stuff. So if people say, well, gosh, Mrs. Frederick, why do I have to take pre-calc? And I'm going to say, well, you don't have to. It's an elective. However, yeah, are you going to remember all these formulas? Probably not, but the idea of persevering and problem solving, yes. I hope that's something that you take on with you into your previous or your next classes, and then in other classes too. Problem solving is what I do all day long, especially with distance learning. All right, so I want to change, my goal is to change this part of the formula or this part of the formula, because I don't know. And this is the honest truth. When you're in class, sometimes you have to do this 7 times before you get to the goal. That is normal, by the way. So how come I know what to do? It's because I'm improving these a long time. So I'm letting you know it's normal for you to have to like trial and error until you get it. That's the problem, is there's no formula for how to get these. All right, so I need to try to figure out, can I get a 1 here? Well, here's the deal. If I can get a 1 there, I have to do the same operation everything else. So if I was to divide this term by cosine A cosine B, I would get my 1. You can see it right there. But in order to do that, to keep the mathematics, to make it make sense, I have to create a common denominator on every term, and that's what I'm going to do next. Alrighty, so I rewrote everything with big spaces for you, and I highlighted what we're going to use to divide. I don't know if it's going to work, and if it doesn't, that's okay, because you need to see basically experiment, right? That's what problem solving is a lot, is you're experimenting or trying to fix something, and you may not get the answer right away, so that's normal. And then cosine B. It's a lot of writing, huh? A lot of letters. Okay, and then you start doing the simplification. And the reason why it's legal to do this is because I'm creating the same common denominator on every single term. This would not work if you didn't have that. That's where the equivalency comes from. Okay, so we're going to start simplifying and hoping for the best. All right, so look right there. There's tangent. And it's tangent A. And then, ooh, look right there. That is times 1. So that's nice. There's 1 again. Remember, you have to check the angles. They also have to match, okay? So just keep that in mind. Ooh, we got tangent again. Only this time it's tangent B. So it's 1 times tangent B. And things are looking up so far to where we're trying to reach that goal. This we know, and we built it to be 1. And then hopefully it'll all work out. So there is right here, because you got to get the A's to match up here. This is tangent A again. And then being multiplied right next to it is tangent B. So then I'm going to go back to my problem and see, oh my gosh, look! On the first try, we actually have what we need. So I'm going to just clean it up. to make it look like the formula that we need, okay? So this is tangent A plus tangent B all over 1 minus tangent A and tangent B. Okay, and then the next one is done in a very similar fashion. I'm going to skip that one, and we will look at that again. But you might want to just practice it right now on your own. Like pause the video right now and write out the tangent A minus B and work that problem out. It's like a check for understanding for you, only it's a self-check for understanding. Will I have to prove these on the test on Tuesday of next week? Yeah, it's very possible you're going to have to prove these on the test. So see me after class if you need additional support. Now we're looking at double angle trig identities. And the way this was written, and I just cut and pasted it off the internet, there really should be a parentheses around this angle so you understand the 2 is really inside the function. Okay, so make sure you don't forget to write that. All right, so we're going to prove these. So remember, we're going to use other identities from that we've proven before this. We're going to use those in order to derive these double angles. So we're going to start with the first one. So it's the sine double angle, so let's go ahead and start that. And I'm starting with the original. And then algebraically, you know that if you have 2, that what you're really doing is adding the angles together, and then that allows us to use the sum of sine angle formula. Okay, just to remind you what's going on. So go back and look at your sheet, and I'm going to go ahead and replace this with that formula. Remember, it's sine A, cosine B, and so on, except we know that the A and the B are the same this time. So this is sine A, and I'm just going to go for it. Okay, so going back, putting in our angles. I mentioned yesterday that multiplication is commutative, so what you really have out here that's going to help us is switching these around, which is completely legal mathematically. So what you really have is you have 2 of these that you're adding together, and that is going to help us get what we need. So it's like if you said this is a cow and this is a cow. You have how many cows? You have 2 cows, but that's not what we have. We have 2 of these sine theta, cosine theta. And then there you go. That's how we prove the sine double angle. And hopefully you can see the graph in your head, because that's something I really want you to be able to make a connection with. So I started this process again yesterday, and we did 2 of these. So we did the top one for cosine double angle, and we derived the bottom one. Okay, we did not do the middle ones, but I'm still going to do all 3. Okay, so I'm going to go through and prove those to you. So we're going to start with cosine double angle. Let's see, so cosine of 2 theta, you know and I know that this is the same thing as cosine theta plus theta. And then we're writing out the formula just to point out the signs are opposite when you're doing cosine. So just reminding you how that works. You look at your cheat sheet, and it's cosine A, cosine B, and I'll put the angles back in a minute. And then sine A, and then sine B. But we know these are the same. Oh, stick with the same color. Okay, and then we have x times x is x squared, but we have cosine this time, of course. Cosine squared theta. and then minus sine squared theta. So there is the proof for this one. So we got 1 down, we got 2 to go. So check that out. Okay, so now I'm going back, and I gave you the tip in class, which is you really should go back and start over when you do these problems. Don't try to use what you have because you're still not processing, okay? And you're going to get confused if you don't start over. So I'm going to model that for you. I'm going to do the next one. I know I just wrote it out. Okay, so this time I'm trying to get the 2 cosine squared theta, and I go, okay, what's the process again? Okay, I know that this is equivalent. I know that I'm going to flip the sign. And I know the formula and how to use it. So let's see here, cosine, and then plus sine theta, and then sine theta. All right, so we're back to exactly where we were. It's just good practice. Gotta go back and fix the sign. Some of you are like, Miss Fred, you did not write the right sign, and you're right. So I fixed it. All right, so here was the tip. If I know I want an expression with all of a certain type of trig function, I have to get rid of the other type. And in this time, with the middle problem that we're working on, I only want cosine. So I only want cosine. I got to get rid of this. So you got to work this right here, the sine squared theta. Okay, so go back and think about, or look at your cheat sheet right now, or your notes. Think about what has a sine squared theta in it. Well, it happens to be, one thing you can look at is the sine squared theta plus cosine squared theta equals 1. It's the Pythagorean identity. Okay, how are you supposed to know that? It's because you know your identities, and you can identify that there's a direct substitution. So this is how it was written in your notes. So I'll make sure I do it the same way. And remember, I want to get sine squared theta. So I can get rid of it, and everything is in terms of cosine. And so that's what I'm doing. And then there's my sine squared theta, and then you can see we're going to substitute that in. So go for it. Hope it's getting easier. Always, you know that's how I feel. Okay, there's our sine. So I'm going to do that substitution now. So 1 minus cosine squared theta. But you got to make sure you put the parentheses around. In fact, I'll do it over here also. Otherwise, the sign's going to get messed up. So it's cosine squared theta. And then you're just going to simplify. You got to distribute that negative through, though. So this is cosine squared theta. And then there you go. Here's 1 cosine squared theta. Here's a second cosine squared theta. So this is 2 cosine squared theta minus 1. All right, so now you have the top one today, the second one, and then the third one's in your notes. But I'm going to go ahead and do it, and there won't be any sound for that part. this is a list right now of, in this video, of what I proved to you, and I've proven all of them. I just want to make note that the Pythagorean theorem, if you remember these three, you get the 9 that are derived, which is what I was talking about in class yesterday. The sum and difference angle formulas I didn't prove again. That was a geometry proof on YouTube that I posted, and then we worked a lot on the double angle. Now here's the thing. These are not the only identities or formulas that you've learned in this section. I'm now going to post the additional formulas that I would expect you to know at this point. So I just want to remind you, you have the even and odd property or identity, because that's what all these are. And then this one we've never really formalized, but have been working on a ton, which is the periodic identity. So just to point out what's going on here, look, here's the angle. And then if you add a period to it, one period of sine, what happens? You get the exact same value. That's what this says. Okay, down here, this is the parent period again. So if we go down 2 pi, you're going to get the exact same value. And then note, tangent, we're looking at a period of pi. It's really important to know those periods. And then likewise, we have them for cosecant, secant, and cotangent. So I'm just reminding you, you have done this identity. So if you see this somewhere, it's something you're going to refer back to. Alrighty, in the next video, I'm going to be teaching you how to now solve equations using these identities. Okay, make sure you go back and you organize yourself and you have a good place to figure out where to find these, like have a system, highlight, do whatever you have to do to process. Okay, good job.